were talking about, we had started talking about conserved quantities for the buoyancy-driven flows. I'll backtrack a bit because the point which we need to make is about the scale invariant solutions that are important, because scaling laws are what you have been hearing about. And so it is important to understand the invariances associated with Navier-Stokes equation. And some of these are pretty obvious. The question of translation in space, translation in time, rotation when it's isotropic, Galilean invariance. These are quite obvious, but the one which I want to focus on and where things become interesting is the issue of looking for scale invariant solutions. And we'll start with the standard Navier-Stokes equation, del T Vi plus Vj del J Vi equals minus del Ip plus nu del square Vi. So that's what we want to do. But before I start on that, let me sort of do something for a minute which all of you are completely familiar with, which is the diffusion equation. Del phi del T is diffusion coefficient times the gradient del, so d del to phi del x squared. I asked the question that is there a scale invariant solution of this? You know what the solution is. The solution for this is 1 over t to the power half e to the power minus x squared over 4 dt. So that's the solution for this equation. And the interesting thing to notice is that it is of the f of x squared over t. So that's the scaling form of this solution over here, that 1 over t to the power half f of x squared over t. And the issue is that could I, could I have guessed this combination x squared over t to begin with? And the answer is that look for scale invariant solutions. And so you write x equal to, so you do a scale transformation, x equal to L x prime, and t transforms as some unknown exponent, L to the power z times x prime, t prime. Put this back over here, and then it is, I don't bother about phi because linear equation phi will, whatever scale factor phi will cancel out. So it is del phi del t prime 1 over L to the power z equals d over L square del 2 phi del x prime square. And if you choose z equal to 2, then this cancels out, and it is the solution is for z equal to 2, you have scale invariant solutions. Z equal to 2 automatically means that the variable that it is x goes, length scales go like t to the power half, and therefore the solutions that you would be looking at of x and t would have the structure 1 over t to some exponent, which you would have to find and still, and then it is the combination, the dimensionless combination that comes into the picture is x squared over t. So that's the standard diffusion equation. This is what you do, and to understand the scale invariant properties of this. And that's exactly what I'm going to do over here. So that's why the so something which you are familiar with, so best to see it with that first, and I'll ignore this part. So to begin with, I'll drop that bit, not Navier-Stokes, just plain and simple Euler equation. So what was the statement? The statement is that I'll consider a scale transformation. X goes to L x prime, t goes to L to the power z t prime. Then v, now I mean it's nonlinear, so I better worry about v going to, so what is, it's x over t, so L to the power 1 minus z times v prime, and so there we are. And mind you, this is incompressible flow, del I vi equal to 0. Therefore, del square p is minus del I vj del j vi. So I don't need to worry about the pressure term. The pressure term won't be doing anything special. It will be the gradient of pressure would have the dimensions exactly of this Vj del J Vi, so nothing needs to be done about that. So there are only two terms that I need to worry about, this chap and this chap over here, and we get to work, and it is del T prime and Vi prime. The factors are L1 minus Z, and it is 1 minus 2Z over here, plus it is Vi Vj prime, that brings L to the power 1 minus Z, del I prime, that's, let's just write it as with a prime over here, that brings 1 over L, and then Vi prime, that brings another factor of L minus Z, equals to the pressure having the same thing. So here we are, it is L to the power 1 minus 2Z del T prime Vi prime plus L to the power 1 minus 2Z Vj prime del J prime Vi prime equals the pressure gradient with the same, I mean it would be L to the power minus 2 del I prime P prime. So scale invariant for all Z. So this just cancels out. So Euler equation has scale invariant solutions. I mean, you can do this rescaling over here, and you'll get the same equation back for any Z. So any Z works. So that's all right. No information, really. But now let's go to Navier-Stokes equation, and I'm going to put this chap back in action. So this is going to be left-hand side now. So that is plus, so I'm going to add this. It is going to be new, and then it is del square, so that brings in L, that's going to be L to the power minus 2, So 1 over 1 over L square, and then it is del prime square, and it is Vi prime, and that brings me another factor of 1 minus Z. And so this is a total of plus nu, and it is del prime square Vi prime, and it is L to the power minus 1 minus Z. So it is L to the power minus 1 minus Z, and therefore the new equation looks like, so let's erase this part over here. So this is going to look like del T prime Vi prime plus Vj prime del J prime Vi prime minus del I prime P prime, plus now it is nu del prime square Vi prime, and it is L to the power minus 1 minus Z, and you bring this 2Z minus 1 from the other side, it is L to the power Z minus 2. So this is what happens under a scale transformation. So Navier-Stokes equation is not scale invariant as it stands, unless you say that, look, I have a funny situation where nu is actually scale dependent, and nu L has the scaling behavior. Nu is really nu L, which is nu 0 L to the power 2 minus Z. And if this were to be true, then you restore so scale invariance is restored in Navier-Stokes equation if it so happened that this nu is the nu that you are starting out with was actually a scale-dependent viscosity with the scale dependence coming as L to the power 2 minus Z, then that would absorb this Z minus 2, and you would be doing all right. Aha. So does that, so what does this, so number one, the point is that what we were interested in last time was this question of inertial range. Remember the inertial range and the scaling, which said that this delta V as R went as epsilon to the power 1/3 R to the power 1/3. We wrote n raised to the power n, and it was like this. That was the inertial range scaling. E of k, the very well-known result, some constant epsilon to the power k to the power minus 5/3. So there were some scaling answers, and then therefore, I mean, if these scaling solutions are there in the inertial range, then the equation that I started out with must have a scale dependence, and that is telling you that the viscosity that you started out with would have to be, that is the Navier-Stokes equation that I need to write down should have a scale dependent viscosity. Is that question is, does that make any sense? Well, what if I were to start right now? What is this? When I go back to this over here, this is the relaxation. I mean, what nu is telling you is the rate at which the these fluctuations are going to, suppose I have a deviation from the steady state, the time scale, this nu times del square is actually the time scale in the problem, and there is it's a relaxation time scale, so nu times del square, which is like in momentum space would be like nu times k square. Nu times k square is the time scale for relaxation. So if I were to have a time scale gamma for relaxation, then gamma of k is nu times k square. I mean, this is, that is, solutions would decay, any fluctuations would decay according to e to the power minus gamma t, which is like e to the power minus nu k squared t. So gamma is dimensionally like a frequency. So that's what, that's what this is. But if I am in the inertial range, and everything is going to be determined by epsilon and k. Now you are in the inertial range and everything determined by epsilon and k, then what is gamma of k going to look like? So then let me say that gamma of k is like epsilon to the power alpha, k to the power beta. So gamma has the dimension of frequency. That's what it is. So it is 1 over t on this side. Epsilon is L squared over t cubed to the power alpha. And this is 1 over L to the power beta. So immediately beta is equal to 2 alpha, and 3 alpha plus beta equals 1. So that's 3 alpha is 1. Makes sense. Now, so alpha is equal to 1/3, beta is 2/3. Thank you. So that's the answer. So this gamma of k, this is like some gamma 0, epsilon to the power 1/3, k to the power 2/3. So this is your gamma of k, the relaxation rate. And if you compare with this relaxation rate, which is supposed to be nu effective square, that tells you that there is a nu effective which behaves like epsilon to the power 1/3, k to the power minus 4/3. So there is a scale dependent. So this says that the if I do a Kolmogorov dimensional analysis on this problem, that the relaxation rate also has to be in the inertial range determined by epsilon and k, then here it is. It tells you that there is a relaxation rate which is like this, and this is the. All right. Now this now I can sort of close the loop. So the scale invariance required that nu of L go like L to the nu 0, L to the power 2 minus z. Nu effective, according to this Kolmogorov, is this. Now, how do I, is there a way in which I can nail down Z, not from what I have said over here, but there is this additional constraint, the constant for Kolmogorov, and there is this physical assumption that constant energy flux, that is energy transfer rate, which is this epsilon, which was dimensionally L square, is scale independent. So scale independent, epsilon is scale independent. So if I do rescaling, so then the epsilon, when it is L prime square over T prime cube, would go to L to the power 2 minus 3z epsilon prime at a different scale is L to the power 2 minus 3z, and scale invariant, scale independent epsilon z equal to 2 by 3. So imposing the constant energy flux being scale independent fixes this scale which I introduced with the time scale, variable as z equal to 2 by 3. Z equal to 2 by 3, well, with z equal to 2 by 3, my nu of L goes as nu 0 to the power L to the power 4 by 3, which is the same as what you have over here. So that's how you close the loop. Scale invariant solutions lead along with the statement that the energy flux is going to be independent of scale, tells you that there are solutions over here, where the solutions that we talked about, the delta V, you can, that it is r to the power 1/3 is obvious because V scales as 1 minus Z, Z is equal to 2/3, so V scales as L to the power 1/3, so that's the r to the power 1/3 over here. This argument does not give you the epsilon to the power 1/3 part of it. That has to come from the dimensional analysis, but just the scale invariance of Navier-Stokes equation requiring scale invariance plus the fact that there is a scale independent flux going through the wave numbers can give you this part correctly, and that follows that this part is obtained correctly and gives you this part correctly, but not this. This has to come from the dimensional analysis. But these are actually, now the point of bringing this up is that it's real. I mean, this is, for years, people have been talking about algebraic K epsilon models, where the turbulent viscosity, so in these models in the 70s, turbulent viscosity was modeled as nu being like equal to some coefficient K squared over epsilon. This the same as the epsilon that we have over here, the dissipation rate. So this is the dissipation rate. This, the kinetic energy, K is the kinetic energy. Total kinetic energy over the relevant scales, and the working model for doing computation with these in high Reynolds number flows was to use this algebra K epsilon model with nu equal to this, and this constant, by playing around, people got as 0.09. So nu equal to 0.09 into k square over epsilon. And the reason I want to point this out is that if you now take this as your the new effective as the scaling argument, which gives you a new effective equal to some constant nu 0 epsilon to the power 1/3 k to the power minus this as a function of k at this wave number. So you can start from this, and the nu 0, that's another story which I won't be able to get into. But the point is that all over the 80s and part of the 90s, people were actually in the business of calculating the coefficients over here. That is, calculate C, calculate the coefficient gamma 0 over here, calculate coefficients like this, calculate coefficients like C, because if you didn't do that, then I mean, it ends at what I have told you, that do some dimensional analysis and get. So where is the real challenge? The real challenge would be to nail down these constants over here. And through the 80s and part of the 90s, people did try and get these numbers. And if you calculated these numbers, then the number that you get for this, you get the K epsilon model, and the number that you would have got over here, this number was 0.084. This was Orszag, Yakut and Orszag. Way back in 86, and that works pretty well. In fact, this number, this constant C over here, which has been measured pretty well. I mean, people measured it over the years and found it ranging from 1.6 to 2.1 or something like that. That was the measured range. People who managed to fit the energy spectrum to the Kolmogorov found a coefficient which goes like that. The calculation of this number gave you something like 1.63 or thereabouts. So there was, I mean, actually some merit in these scaling calculations and a more detailed business of actually getting these numbers, which fell into disrepute for reasons which I'll also mention. Primarily the point being that, look, I mean, everything is multifractal, so this 5/3 is an illusion. There is a correction. As soon as there is a correction to this if the 5/3 is not 5/3, but even 0.01 away from it, a number like the dimension has no meaning. So if you are going to accept that there is a small correction over here, and the correction becomes larger as the delta V, if n increases, the corrections they vanish at n equal to 3, as I said, because that's exact, but they become the corresponding corrections, that is deviation n over 3 plus delta n. These numbers become larger. So there are, but over here, the correction is, but once you accept this, constants and any calculations of constants and so on are in principle meaningless. In practice, I mean, what was lost, I think, in the decades that followed, that there was a starting point. And it's very obvious why which I'll tell you in a few minutes, why the starting point was not quite right, why there is a lot of complication with the starting points. But as some kind of an approximation, it is still pretty good. So anyway, I mean, the point is this is scale invariance. There is a scale invariant solution of Navier-Stokes equation. And if you couple that with the fact that there is a constant energy flux, then you have this Z equal to 2/3 and the Kolmogorov business. And things fall apart because the fact that this constancy of energy flux through the scales is what is not quite right. There is fluctuation around the mean over here. So there is effective L dependence, scale dependence. There is fluctuation in this epsilon and the consequent scale dependence, which is the source of all difficulties, but that is all right. I mean, that's scale invariance. This is what scale invariance is as it stands, and I mean, you get practical answers if you from it if you impose the Kolmogorov. So that's the time domain meaning. I mean, we are in steady state. Oh, the frequency domain, I mean, that's straightforward. If I have if I can define a mean flow, then k to the power minus 5/3 has to go to omega to the power minus 5/3. If I don't have a mean flow and carry out a scaling argument of the frequency, it's 1 over omega squared. So that's just do a dimensional analysis, say that, I mean, define the frequency domain and ask for epsilon and omega dependence. It would be omega 1 over omega squared. And all right. But if it is still a hypothesis, it's 1 over omega to the power 5/3. All right. So that's the thing over here. So actually, it's I want to just write down. Maybe I mean this is something which you can think about, and the answer would be there tomorrow. That what would happen? What would be the, if I were to analyze do a scaling analysis of the kind which I just showed you, if it is the buoyancy-driven flow, and you start with what we have been talking, all of us talking about in various form or another, the same, but there is alpha t delta t theta, never mind sines. So if you started out with this, and if I did the scale, if I looked for scale in variant solutions, then mind you, I would have to do, there is this extra field over here. So as we found, so L, the spatial is x going to Lx prime, v goes to L to the power 1 minus z, v prime t to t to the power L to the power z T prime, and then there would have to be theta going as some L to the power y theta prime. That's an additional field, so I have to put in a additional scale factor for that over here. And the issue would be and the issue would be looking for scale invariant solutions over here. There would be now a question of two fluxes. There is epsilon because the kinetic energy flux, and there is epsilon theta, which is the theta square flux. So there are these two fluxes, there are, this additional field. Question is, what does it look like and what do you get? So that's something which you can play around with tonight, and tomorrow you can compare with what at least my take on that is. And all right. So is that, so this is a point to stop this line of scaling arguments and change to a different buoyancy-driven flows and a different scaling. So is that, is this clear up here? Any queries which you might have, I would like to handle now. Sure. That's what one needs to find out, right? That is what there is, mind you, nu, there is the thermal kappa, there is also the expansion coefficient. That, you'll have to just go through and see. All right. So going to change to flows which the issue which Richard Stevens has talked about at great length, and I'll use the next half to give you some heuristic answers, which at least I'm not sure what they are very good for, but they are entertaining. So let's keep it at the level at which it should be kept. So all right, so there is this convective layer. I have a temperature T1 on this plate. I have a temperature T2 over here, which is T1 minus delta. I have a T, so this direction is Z. I have T versus Z plot over here. And so this is, things start at T1, things finish at T2 equal to T1 minus delta T. And the profile is, so that's some scales here, D. Good. So it starts at 0, ends at Z equal to D, and profile initially is so something which Mahendra Verma has talked about, and Richard has talked about, and the conduction state, and T is equal to T1 minus delta T over T times Z. So there we are. a linear profile. This conduction state gets destabilized at R critical, which is something like, depending on what, it's 27 pi 4 over 4. If it is idealized no-slip boundary conditions, it's 1708. If it is both rigid, both walls rigid, that is no slip, this is free slip on both, then there is a combination of rigid and free slip giving you an answer in between, and so on. So, all right, now at RA greater than RA critical, you have the issue of convection. And one is then, before the convection began, this was all the heat transfer. So for RA less than RC, the life was easy. Heat transfer was heat transfer by conduction. And that's the rate of transfer is lambda T over D. So the rate at which heat is conducted transferred from bottom plate to top plate is this lambda T over D, and no questions asked. Now comes the question of RA greater than, there is heat transfer by conduction, and so plus heat transfer by convection. So this part for RA greater than RC. And one then comes up with the question of how much by convection, how much by conduction. And there is this Nusselt number NU, which total heat, total transfer from, that's transfer of heat from Z equal to 0 to Z equal to D divided by conduction transfer. All right. So this is equal to 1 plus transfer by convection divided by transfer by conduction. So that's now, when it just started, when you are close to RA is RAC, so this is equal to 1 plus epsilon, epsilon is small. That's when you are comfortable in calculating. And you can easily write Nusselt number as 1 plus some alpha times alpha 1 times epsilon, alpha 2 times epsilon square, and so on and so forth. And you can, for all you are worth, get these coefficients alpha 1, alpha 2, and so on. And near the threshold, life is easy and comfortable. So a little bit of drudgery, and numbers like alpha 1 and alpha 2 can be found. They agree with experiments, they give you confidence, and life is very pleasant. It's when you are breaking away from this vicinity of the threshold that life becomes complicated, because you don't know. Calculational tools are not there anymore. So it has to be by default, the answers have to come from numerics, simply because the patterns of flow become much too complicated. You can at best tackle one or two after this threshold if you are very good at guessing what kind of, then you can get one or two of them, but generally life becomes, if you are going to go beyond epsilon equal to 1, life is complicated, and it is, at the end of the day, numerics is the only answer. So therefore, I mean, there is a whole range where, I mean, you can't, you don't even know how to get started. But then, when this Rayleigh number becomes much greater than RC, so RC, RA critical is like 10 to the power 3. If I'm now looking at RA greater than about 10 to the power 5, then this temperature profile changes, and changes, I mean, changes dramatically. It keeps on changing, but this in this large Rayleigh number range, the change is dramatic, and as soon as this change is dramatic and things begin to look somewhat tempting, let's say. So here it is for T over here. So this is your T1, this is your T2, and what it looks like is this, and it looks like this. So there is this L, small region L, so this small region L near each wall. So here we are. This is Z equal to 0. This is Z equal to D. The action seems to be near these walls over here. So this is Z equal to D minus L. This is Z equal to L over here. And that's, the action seems to be concentrated near these, in a small layer, the so-called boundary layer, simply because it's near the boundaries. So it's in this small layer over here, where it's where action, at least the thermal action, seems to be going on. Most of the half of the temperature drop is across this level layer over here. Other half is and it's a more or less uniform temperature somewhere in the middle. I mean, not exactly, but well, I mean, as a guide to doing something or other. So this, I mean, this simplification brings great joy, that now, I mean, you can be back in business with heuristic arguments. That's the whole game, that one has to understand the spirit of these calculations, that it's a question of essentially looking at this simplified. So, all right, great. So what, as you have seen over the last couple of days, I mean Tuesday's lectures by Richard Stevens, that this Nusselt number has scaling behavior, but people are interested on what this number is. There is a question of Prandtl number dependence of this as well. So Nusselt number how does it depend? I mean, a scaling behavior, once again, with respect to Rayleigh number. There is maybe some scaling with respect to Prandtl number, but at least there is, let's say, scaling behavior is not a bad idea. So as soon as there is this evidence that scaling ideas are not too bad, you can start getting into action. So it's what is the action going to be? So action is going to be that Nusselt number is total transfer from z equal to 0 to z equal to d divided by. All right. Now, what's the amount of heat which is leaving this boundary over here? The amount of heat which is leaving the boundary, so amount of the rate at which heat is leaving z equal to 0 has to be, I mean, dt dz at proportional to lambda dt dz at z equal to 0. And what is this dt dz at z equal to 0? If L is small enough, then this is like lambda delta t over L. And what is conducted from here to here? The conducted amount is always delta t divided by d. This is the amount of heat conducted regardless. So that tells you that I can get the Nusselt number by calculating d over L. So amount of heat transfer, because that what is leaving over here has to get over here. So that's straightforward. So what is leaving is equal to what is transferred from top to bottom. So what is transferred is proportional to delta T over L. What is transferred by conduction is delta T over D. So the Nusselt number, which is the ratio of the total to the conduction alone, has to be like e to the power L and scales like this. So that's the, so now the basic question is what, how crude can you be to get beta? So the first shot, which was already actually pretty good, was to say that look, this is, I have a local Rayleigh number, local Rayleigh number for the boundary layer. The overall Rayleigh number is defined by RA equal to alpha g delta t d cubed over lambda nu. That's the Rayleigh number that one is. But there is a local Rayleigh number in this boundary layer over here. That has to be RAB, which is alpha g delta t times L cubed divided by lambda nu, which is equal to L cubed over d cubed times RA. So now what is this, what do I know about this Rayleigh number of the boundary layer? Well, this boundary layer is stable, so it exists. If it does exist, then that Rayleigh number at best has to be set pegged at its limiting value, which is something like 10 to the power 3. So at the end of the day, this is some number around 10 to the power 3, and therefore d over L goes as RA to the power 1/3. So Nusselt number scales as RA to the power Rayleigh number to the power 1/3. This was 1954. And gets a huge part of the story. So, and it's now the point with the mid-80s was that if I look hard enough, and if I'm way beyond 10 to the couple of magnitudes or more above 10 to the power 5, then the point was that it is not 1/3, but something smaller. So Rayleigh number of the order of 10 to the power 8 or greater. What you saw 2 days ago was Rayleigh number up to 10 to the power 13. And here it is Ra to the power something which was less than 1/3. This late 80s, mid 80s to late 80s, the point when this was driven home were a set of experiments, which is Kasteng, Gunaratne, so on and so forth, Libschaber, Karanov, so on. So that huge, very interesting piece of work, and where there was a different way of calculating this exponent, which actually looked at more carefully the nitty-gritty of the transfer processes over here. So so this argument went like this. So the argument now was that, look, number one, I mean, this obviously is not flat. There are fluctuations, delta t, around this flat region. So there is delta t, which is over here. The fluctuation delta t around the sort of flat central value, that delta t was something which became, the observation was that it became smaller as the Rayleigh number increased. So the delta t became smaller with increasing Rayleigh number. And the way to characterize delta t, of course, is through the ratio delta t to the real delta, the whole delta t, so the fluctuations relative to this. And they had to fall off as Rayleigh number increased, and it was characterized as Ra to the power delta. If I have purposely written it as Ra to the power delta, because then at the end of the day, if everything is consistent, delta should turn out negative, because that's that would be the expected what Libschaber and company saw, that the fluctuations around the central value diminished, relative fluctuations diminished as you increased the Rayleigh number. So this delta should work out to be negative. All right, very good. So what's then the magnitude of the velocity in the center of the cell? So here is the cell once again. Those are the two real boundaries. These are the boundaryless, and in this middle over here, the velocity scale, if it is some w, then obviously w square and has to be like alpha W has to go like alpha G delta T times D. So that's your W squared. So W goes as this to the power alpha. So that's the scale for W. So if the thermal fluctuations delta T producing a velocity in the center of the scale for that velocity is this. If W then goes as this is R delta T, so this is RA to the power 1 plus delta by 2. Right? So this is delta T over delta into delta T. Delta T is RA to the power 1, so it is 1 plus delta. So W scales as 1 plus delta by 2. All right, good. So that's in the center of the cell over here. Now what about the force balance? Force balance in the boundary layer. The force balance in the boundary layer would be that your viscous drag, which is the boundary layer is small, so this viscous drag is the important term. So this balances the buoyancy force, which is alpha G delta T. So that's the next argument, that W over L squared goes as this. Now that means that W, this is going to give you another estimate for W. You have, so 0 over here, W over here after a length L. So nu del squared velocity is estimated as W over L squared. So this is like RA to the power 1 coming from here. And then it is L squared. So this is 1 minus 2 beta. Right? So L square is like 1 over L square is like 1 over L is like beta. So 1 over L is like R to the power 2 beta. So L square is like minus 2 beta. So that is that. W, on the other hand, I have just said that RA to the power 1 plus delta by 2. Therefore, 1 plus delta equals 2 minus, so delta is 1 minus 4 beta. So that's the force balance in the boundary layer. Now what about the heat balance across this boundary layer? The amount of heat which is reaching heat balance is the amount of heat reaching per unit time. So amount of heat reaching the top of the boundary layer. So this is the top of the boundary layer. Amount of heat that has reached it is like lambda delta T to the power L. And there is no accumulation, so it has all been convected away. All convected away. And the convection is going to be like the operational things in the center of the cell. So that's like W times delta T. So you have another situation where this is RA to the power 1 plus beta on this side, and this is W, which is RA to the power 1 plus delta by 2, and delta T over T, that's your RA to the power delta. This is 1 plus RA to the power delta, and there is RA, so there is a 1 plus over here, which, I mean, the delta t over delta t, those delta t's actually cancel. So this is beta equals half plus 3 delta by 2. So there we are. I have delta 4 beta plus delta equals 1. And from here, I have 2 beta minus 3 delta is equal to 1. So I multiply by 3 over here and add. So if I multiply by 3 and add, that is 14 beta is equal to 4. Beta is equal to 2 by 7. And if beta is 2 by 7, then delta is equal to minus 1 by 7. So minus 1 by 7, which at least, I mean, as I told you, that delta had better turn out negative. So delta has turned out negative, and this is minus 1 by 7. So the things are consistent, and beta has turned out to be 2 by 7. Nusselt number goes as RA to the power 2 by 7, which is a number which is less than 1 by 3. So this was the argument which Lipshaber, Kastank, Kadnoff, and so on had, which gave you the inkling of why there should be a number smaller than 1 by 3, which is this. But this doesn't tell you anything about a Prandtl number dependence. The Prandtl number dependence was a few years later. This was a different kind of approach. Siggia in, I think, 93, 94, somewhere around the time. And this started looking at it a bit more carefully, saying that, look, I mean, let me rewrite the, let me change the starting point a little bit. Let there be some relations which are robust, and some relations where where things are not so robust. All right. So this said that let me write the Nusselt number, start with the Nusselt number as being the buoyancy flux by the conduction, heat conduction flux. So write it in this manner over here. Why is this important issue? This is an important issue because the last thing which I did on Monday showed that in these convective things, there was a conservation law was that ddt of the energy, this energy minus this buoyancy part, this quantity was equal to 0. So the rate of change of energy was the rate of change of this buoyant energy. This is the buoyant energy. Let me put it as some bar or something or other. So the rate of change of this is what we saw as one of the last things on Monday. So you use this to write this as, this is like an energy, this can be related to the energy flux epsilon. So you are using, so this is d dt, the rate of energy input, which is this epsilon, and you are going to relate this Nusselt number defined in this manner to the epsilon which we have talked about. So the identity that he obtained under this condition was that the Rayleigh number times the Nusselt number. So this was your alpha g delta t d cubed over lambda nu, and there was there is this epsilon over here, and there is this point x, which is this lambda t divided by d, and so the delta t cancels out, and you have Ra times Nusselt number go as the alphas and the g's are not so interesting. It is d, there is a t cubed, epsilon, and there is a d, and there is an alpha g, which is, as I said, I'm not particularly worried about, and there is lambda square nu. All right? So that's, now, recall that epsilon, the rate of energy, is like some velocity v divided by d cubed. So that was the whole business. Sorry, I got it all. V cubed over d. So epsilon d was like the, this is the rate at which you are pumping energy into the system. So that we estimated as v cubed over d, v square over t square, and v square over t cubed, and then, I mean, playing games with that. So it's v square over t is L by v, so that's, I mean, v cubed over. So all right, so that's that. That tells you that this epsilon d over here is actually, so alpha g I'm going to drop. Epsilon d is like v cubed. There is a d cubed, and over here, if I put nu cubed over here, then this is nu by lambda square, which is like, this is the Rayleigh number, Reynolds number cubed, and here is the Prandtl number square. So this was the big issue, one of the interesting Siggia results, that this is Re cubed PR squared. So that was the starting point that I have by using this definition of the Nusselt number as buoyancy flux and conduction flux. The ratio gives me this identity. Well, identities meaning apart from numerical constants, that Ra times nu goes like that. All right, now look at the here transfer. Now comes the next assumption. So this was point number one. Point number two was that the momentum boundary layer is much significantly wider, bigger than the thermal boundary layer. So momentum boundary layer significantly larger than, so that when I talk about this region over here, this is the boundary layer that I'm talking about. The momentum boundary layer is somewhere over here. So in this range, in this boundary layer over L, the velocity, the parallel velocity all velocities vanish at the plate, and then u, the horizontal velocity, is still linear profile. So it is linear profile for the velocity, and because the momentum boundary layer is, so all the logs and so on would be coming later. So it is still a viscous sublayer, and u is still linear, which means u can be written as u0 square. u0 is some scale. It increases linearly and dimensionally. So it is u equal to u0 square z over nu. So that's the profile for u. And what is the temperature balance? The temperature equation in the boundary layer, that's going to be, in the presence of this u, it is del T del X goes as some lambda, the thermal conductivity, that's del to del Z square. So u del T del X, so that's the temperature equation. Essentially u dot, we are looking at V dot del T going like lambda del square T, the temperature variation primarily in this diffusive part along the Z direction, that's the dominant chap. The u has in the horizontal velocity has increased significantly in the viscous sublayer, and so it is this balance over here, which means that it is u0 squared z del T del X divided by lambda nu goes as del to del Z squared. So u0 squared z over lambda nu goes as this, which tells you that there is the scale, there is a z cubed, which is the same as x. So the scale that you are essentially looking at, z cubed has to be compared. What does z cubed compare with? Z cubed compares with lambda nu times x divided by u0 square. So that's the comparison scale, that the scale of z and the scale of x are related by this relation over here. Thereafter, you can, I mean, as Siggia does, write down the, try to write down an approximate solution and so on and so forth, but that's, but you can argue from here that by the time, I mean, your x, so if you are talking about a small container, aspect ratio of the order of 1, then when x is going to be of the order of d, z is going to also reach d. So x reaching, x tending to L, D was the wrong choice of words. X tending to, no, it was the right choice of words. X tending to D, that is, you reach the aspect ratio, the width of the, by the time you reach that, in Z, you reach the height of the boundary layer. So it is L cubed going as lambda nu D divided by u naught squared. So that sets up another equation which you have to which you can deal with. So it is L cubed going as lambda nu D divided by u naught squared. And in addition, you have this result that you always have, which is this. So this is complemented by this additional answer over here, where now you can use this to get your Nusselt, another relation. This will give you another relation between Nusselt number and Reynolds number. This will give you another relation between Nusselt Reynolds, and so I'm getting sort of a bit tight over here. So this is going to be a relation between Nusselt, Reynolds, and Prandtl number. Eliminate Reynolds between this, and the answer that should come out is the Siggia result for this is eventually, it's just a bit of algebra, and you will be able to get the answer. Nusselt number is Ra to the power 2/7 divided by Prandtl. So that was the Prandtl number dependence. So this extra bit, by looking at the details of the transfer process, what Siggia could arrive at is the Prandtl number dependence of the Nusselt number in this region. So that was, so it was a Rayleigh number to the power 2/7, Libschaber and company, and then Prandtl number dependence coming over here. So finally, the last bit, since I have got everything virtually set up for it, remember that all this was with the existence of a boundary layer, which was a laminar boundary layer where the temperature had this nice linear profile. So that was the conduction process where this temperature had a nice linear profile, the only conduction taking place over here. Now, there was this in Professor Stevens' talk a couple of days ago, that there is finally the regime where the laminar boundary layer becomes turbulent. And what he very clearly showed that what this meaning of this is that the advection scale is same as the diffusive scale, so that if I'm looking at it's the same scale which I have for the diffusive range over here, and the same for, so if I'm looking at this temperature balance, then it is V, and then it is delta T divided by L. That's the balance over here, which is going to be your lambda delta T divided by L squared. That's the order of the diffusive term, and therefore now it is a question of V times L, V times L over lambda. That's of the order of unity. So it is VL over lambda, order of unity. This V, once again, one goes into business with the fact that you want to bring in the nu, you want to bring in VD L over D divided by nu, and nu over lambda, that's of the order of 1. So here is your Nusselt number, here is your Reynolds number, here is your Prandtl number, giving you another relation between, just as this gave you a relation between nu, Nusselt, Reynolds, and Prandtl. Over here, once again, you have, here is your Reynolds, here is your Nusselt, here is your Prandtl, and so you have a relation between these three. Eliminate, this is always valid, so this is always valid, and so between the two, eliminate your Reynolds number, and you will find that Nusselt number goes as Ra to the power half PR. So this is with the here's the turbulent boundary layer. Supposedly, I mean, characterized by the fact that your advection scale is the same as the diffusive scale, and that, as was shown in the lecture on Tuesday, that it is not really, I mean, this is not the Krishnan answer. It is the Krishnan answer so far as this half is concerned, but the Krishnan answer, which requires really a fair amount of work, has this logarithmic factor associated with it, and so the so-called ultimate regime is really a question of this modified by it, but trivial calculation of, by using the physical concept which was pointed out, that the advection scale is the same as the diffusive scale when it is a turbulent boundary layer. The nonlinear terms are equally strong over there, gives you at least the Ra to the power. So this is the kind of scaling arguments that you can play games with, build some pictures, and if somebody else tells you what things actually the details look like, thereafter you can, I mean, after the event, you can come in and play a few games. Some answers would be reasonable, some not so reasonable, but at the, it's always a kind of entertainment in some sense. So thanks very much. I mean, there are, I mean, issues which we have not touched upon, primarily what went wrong with calculations, and but that's a technical issue, or you may not even be wanting to know the answer. So let's stop over here. That's